Lesson 5, Newton's second and third laws of motion. Newton's second law of motion. If the net external force on an object is not zero, then the object accelerates in the direction of that net force. The magnitude of the acceleration is directly proportional to the net force and inversely proportional to the object's mass. What that last statement means is that the larger the force on an object, the larger the acceleration will be. But the larger the mass of the object, the smaller the acceleration will be. If an object is small, it's easier to get it to accelerate. If an object is large, it's more difficult to get it to accelerate. It requires more force. Newton's second law can be summarized with this one equation, which states the net force is equal to the mass times acceleration, where m is the mass, and the mass is measured in kilograms, and acceleration can be reported in meters per second squared, or an equivalent unit is newtons per kilogram. These two are the same. Both meters per second squared and newtons per kilogram are interchangeable. For this unit, since we're dealing with forces, which are expressed in newtons, the unit newtons per kilogram is a more practical choice when describing the acceleration of an object. Let's take a look at sample problem number 1. A net force of 58 newtons west is applied to a water polo ball of mass 0.45 kilograms. Calculate the acceleration of the ball. So we have a water polo ball. And there is a force applied on the ball, and it's in the west direction. And it has a magnitude of 58 newtons in the west direction. So we're given the net force, and we're given the mass, and it's in kilograms. If the mass is not in kilograms, you'll need to convert it into kilograms. And what we want to find is the acceleration of this water polo ball. So we know our equation states that the net force is equal to mass times acceleration. We can rearrange this equation by dividing both sides by m. These will cancel out, and we are left with acceleration is equal to the net force divided by the mass. So that's 58 newtons west divided by 0.45 kilograms. If you punch that into your calculator, you'll end up with an acceleration of 129 newtons per kilogram west. Another way to report this is the acceleration is 129 meters per second squared west. Both of these are equivalent because newtons per kilogram and meters per second squared, as we mentioned above, are interchangeable. They are equivalent. Let's try a second example. In an extreme test of its braking system, under ideal road conditions, a sports car traveling initially at 26.9 meters per second south comes to a stop in 2.1 seconds. The mass of the car with the driver is 1.18 times 10 to the power of 3 kilograms. Let's calculate the car's acceleration. First thing we'll need to do is to write down all information that is given in this question. And we have to be careful that we get it all. Some of the information is explicitly stated, and some of it is implied, and you'll have to make inference from what you read. So let's take a look. Let's start with the first piece of information that's given. It's 29 meters per second south. So this is the car's initial velocity. So initial velocity is 26.9 meters per second south. They tell us that the car comes to a stop in 2.61 seconds. Now there's a couple of pieces of information that are present in that one statement. Number one, the elapsed time is 2.61 seconds. But the other thing they tell you, and this is really important, I mentioned it in one of the previous lessons, they tell you that the object comes to a stop. If they tell you that the object comes to a stop, this implies that the final velocity of the object is 0. Okay? So what they want us to find first is the object's acceleration. And acceleration is equal to delta v over delta t. We know that delta v is the same thing as v final minus v initial over elapsed time. So we can sub in our values. That's 0 minus 26.9 meters per second south, divided by an elapsed time of 2.61 seconds. If we punch this into our calculator, we end up with an acceleration of negative 10.3 meters per second squared south. Therefore, the car's acceleration is negative 10.3 meters per second squared south. This negative sign implies that the car is decelerating or slowing down. Okay, in part B, we need to find the net force needed to cause the acceleration that we just calculated in the car above. So we know that the net force from Newton's second law is equal to mass times acceleration. The mass of this vehicle is 1.18 times 10 to the power of 3 kilograms. And the acceleration we just calculated was negative 10.3. And then watch what I do here. So instead of writing meters per second squared for the acceleration, because I'm dealing with forces and I want to calculate the net force, I'm going to instead use newtons per kilogram as the unit for acceleration, because remember, meters per second squared and newtons per kilogram are equivalent. We know the direction here was south. So let's punch this into our calculator. If we do, we end up with negative 12,154 newtons south. Now, a force that has a negative sign can be rewritten if we change the sign and change the direction. So that means that in order to get this car to slow down, we need to apply a force of 12,154 newtons in the north direction. Negative 12,154 is equal to positive 12,154 newtons north. So negative south and positive north are equivalent. Now let's take a look at Newton's third law of motion. Newton's third law of motion states, for every force, there is a reaction force that is equal in magnitude but opposite in direction. Some examples. The apple pulls down on the stem of a tree while the stem pulls upward on the apple. So we have the apple pulling down on the stem. This is called our action force. And for every action force, there's an equal and opposite reaction force. And that one is that the stem pulls up on the apple. This is our reaction force. And notice, this one is down, so the reaction force is in the opposite direction always. Okay? So the pull of the Earth's gravitational force pulls down on the apple, while the apple's gravitational force pushes up on the Earth. For every single force, there's a reaction force that's going to be equal in magnitude, but opposite in direction. So let's take a look at some examples of Newton's third law. When swimming, your arm exerts an action force backwards on the water. And the water exerts a reaction force forward against your arms and legs, pushing you forward. So if you need to swim forward, you have to push backward against the water. And that will make the water push you forward. So if we identify the action and reaction force, so the action force is your arm on the water in the backward direction, and the reaction force would be the water on your arm in the forward direction. Whatever force you push on the water will push onto you. That's Newton's third law. Let's look at another example. When a car accelerates forward, the tires exert a backward force on the road, and the road exerts a forward force on the tires. So in order for a car to move forward, it needs to push back onto the road, and the road will push it forward. So the action force is the force of the car on the road in the backward direction, and the reaction force is the force of the road on the car in the forward direction. Our third example explains how a helicopter works. The blades of the helicopter exert a downward force on the air, and the air exerts a reaction force upward on the blades, sending the helicopter into a direction opposite of the motion of the air. So our action force is the blades of the helicopter on the air in the downward direction, and the reaction force would be the air on the blades of the helicopter in the upward direction. So your job is to, with every described motion, be able to tell me what the action force and reaction force is, just like we did in these three examples. What I want you to try are some practice problems for Newton's second law and some practice problems for Newton's third law. When you're done, there will be an LMS quiz that corresponds to this note. Good luck.